This is the review questions that were asked last night on the Jamboard for your Unit 5 test. I'm going to go through and do solutions and post this up so that you guys can watch them today to double check your solutions while you're studying. Now, the first one is page 98, number 7, and it says find the points on this graph where the slope of the tangent is negative 12 over 25. So we know slope of the tangent, that's the derivative, so I'll take the derivative of this function. Using the quotient rule, we've got the denominator times the derivative of the numerator, which is 3, minus the numerator, so 3x, times the derivative of the denominator, which is just 1, all over denominator squared. And we want to know where the slope of the tangent is negative 12 over 25. So I'm just going to put that in, 25. And then simplify out the top. So here I get 3x minus 12 minus 3x. So that's kind of nice, over x minus 4 all squared. So negative 12 over 25 equals negative 12 over x minus 4 squared. And it is kind of nice that we've got a negative 12 on both of the tops. So what we're really looking for is where is x minus 4 squared equal to 25. If you didn't spot that, you can always cross multiply, which maybe I'll do because it's kind of a more straightforward method, and you may not always have that kind of equal numerators there. And this would just end up dividing out. So that would be negative 300. And then divide out by the negative 12, which of course will get you back to the 25. So here I have x minus 4 squared is 25. Square root of both sides, so x minus 4 is equal to plus or minus 5. So two possible solutions, if x minus 4 equals 5, or x minus 4 equals negative 5. If you didn't spot this doing the square root, you could, of course, FOIL out the x minus 4 squared, bring the 25 over to the other side, and it would be a quadratic that you could factor. So here we get x equals 9, or x equals negative 1. So those are the two x values. But one thing to be kind of cognizant of, that if it says points, a point is not just an x value, you need an xy coordinate pair. So I am going to have to take this x value and sub it back into the original function to find y. So 3 times 9 over 9 minus 4, which is 27 over 5. And then the second one, I'd have 3 times negative 1 over negative 1 minus 4. So negative 3 over negative 5, or 3 over 5. So the points, rating them as actual points, 9 and 27 over 5, or negative 1 and 3 over 5. So if it just says find the x values, you could stop after the x equals 9 or negative 1. But if it says points, that always means the coordinate pair. Okay, and here we are looking at B in particular. So if it has a tangent that's horizontal, that means that y prime equals 0. So we're going to figure out where that happens. And I do think this is doable as it is, but we can actually simplify the original function to make the derivative a lot easier. Yeah, probably I would try to, just kind of planning for space here. The original function will factor like that, and we can reduce this, and I'm going to put restrictions on my original function that x is not equal to 1 or negative 2. So if I got any of those. So now if I have x plus 1 over x plus 2, that's a lot easier to take the derivative of. if you didn't spot that, you could still obviously do this. You would just get a messier derivative with a bigger numerator and denominator. So I've got the bottom, x plus 2, times derivative of the top, which is 1, minus the top, x plus 1, times the derivative of the bottom, all over x plus 2 squared. So here I get x plus 2. Make sure you distribute this negative into that bracket. So minus x minus 1 over x plus 2 squared. Oh, interesting stuff is happening here. So this ends up being 1 over x plus 2 all squared. And if we want to know where is y prime equal to 0, can we ever have, think about what we're doing here. We have 1 divided by a function. 1 divided by anything is not 0. This in particular always has to be positive because it's squared. So we could say y prime is greater than 0 for all x values. So then there would be no horizontal tangents. Just kind of stating that that derivative can never be a negative or a 0. Okay, these I think were just all straightforward derivatives. So we'll work through these. On page 110, number 4, there was a few. And quotient rule again. We start with the bottom times the derivative of the top, which is going to be 6x squared, minus the top, 2x cubed minus 1, times the derivative of the bottom, which is 2x, all over the denominator squared. And then cleaning this up, simplifying things out a little bit, I get 6x cubed, now minus 4x to the 4th, and plus 2x. So careful here with this negative. I'm kind of thinking of this as a negative 2x and multiplying it into that bracket. And then on the bottom, I'll have x to the 4th. I have a common factor of x on top, so I get, actually just kind of rewriting things because I've got an x to the 4th. I'm going to take out a negative x and shuffle the order around just to kind of put it in a better form. 4x cubed minus 6x squared minus 2 over x to the 4th, and then reducing out the x. And we'd have an x cubed in the bottom there. So reducing that out. If this was just a quadratic or a factorable, I would keep going, but I can't factor that. Well, I wouldn't expect you to factor a cubic. It might actually factor. I think it does. So this one, remember, whenever we have a square root, you don't want to keep working with it in that form. So make it x to the 1/2. And then x cubed minus x. Different things you can do here. I might actually factor out an x and combine it together with that, but I think likely people probably would not have seen to do that, so I'll try to I'll just do it this way and factor at the end. So g prime at x. Now we have the first factor, x to the 1/2, times the derivative of the second, which is 3x squared minus 1, plus the second, x cubed minus x, times the derivative of the first, which is 1/2 x to the negative 1/2. Now cleaning this all up, I get x to the 1/2, 3x squared minus 1. Here's where I'm going to factor out an x from this. And then I've got 1/2 x to the negative 1/2 times x that I'm factoring out. And I get x squared minus 1. Now I can combine these ones together. X to the negative 1/2 and x to the 1, that's actually x to the 1/2. Now I have a like term of that x to the 1/2. I'm also going to pull out the 1/2 coefficient. So now I have 2 times 3x squared minus 1 plus x squared minus 1. And I can clean up what's in that big square bracket because I'm likely to have some like terms. So this is 6x squared minus 2 plus x squared minus 1. So 1/2 x to the 1/2. And now I get 7x squared minus 3 in the bracket. So I've gotten that to a point where it would be relatively easy to solve for the zeros of that function. Okay. This one, again, this is similar to the other one where I could factor and reduce, but let's do this maybe the long way because I think that that's likely how people would have tried it, and see if we can still simplify that out. And I'll maybe do it both ways. So the denominator, x plus 4, times the derivative of the numerator, which is 2x plus 5, minus the numerator, x squared plus 5x plus 4, times the derivative of the denominator, which is just 1, over x plus 4, all squared. Now I will FOIL this all out, simplify things as much as I can. So here I've got 2x squared plus 5x plus 8x plus 20 minus x squared minus 5x minus 4. Oh, don't forget your denominators. I've said this in class and I just almost did it. We get so focused on like the big mess that's in the numerator, it's common to just miss writing out your denominator and forget it even exists because it's all nice and factored already. Okay, so on top we've got x squared plus 8x plus 16 over x plus 4 all squared. And then this will factor on top, x plus 4 squared over x plus 4 squared. So the derivative just equals 1 because that will reduce. Now I could have done that an easier way if I had rewritten this original function by factoring. So this is x plus 4 times x plus 1 over x plus 4. So the original function, if you reduce those, is x plus 1 where x is not equal to negative 4. So this whole function is a line with a hole at x equals negative 4. So the derivative of that is just 1. So it would have been easier to do this way, but it totally pops out if you do your factoring and reduce, doing it the longer way. Okay, determine all coordinates where the tangent to this curve is horizontal. So of course we know that that means that the derivative is 0. So I've got a product rule derivative to do here. So the derivative is the first, x squared, times the derivative of the second, which is e to the negative x, times the derivative of the exponent, which is negative 1, plus the second, e to the negative x, times the derivative of the first, which is 2x. And then clean this up and factor. So I'm going to common factor out. I've got x's, I'm going to common factor out 1x and also an e to the negative x. So I'm going to common factor out negative x, e to the negative x, and then I will be left with x minus 2. So I know that the derivative equals 0 at x equals 0 or x equals 2. Now remember that that you would need the actual points. If it says points, that's x, y coordinates. So for the first one, if x equals 0, y equals 0 squared times e to the negative 0. We've got that 0 coefficient, so it's just 0, 0. So the point is 0, 0 there. If x equals negative 2, y equals, or positive 2, pardon me, 2 squared e to the negative 2, so that's 4 times 1 over e squared, or 4 over e squared. So this point, x is 2, y is 4 over e squared. Or you could put 4e to the negative 2, that's fine as well. This one is a good thinking question, kind of like looking at the relationship between the derivative and the original function. So let's look at what the derivative would be before we try and prove that. So this will be the denominator, e to the 2x plus 1, times the derivative of the numerator, which is e to the 2x times 2, minus the numerator, e to the 2x minus 1, times the derivative of the denominator, which is e to the 2x times 2, all over the denominator squared. So here I've got 2e to the 2x times e to the 2x plus 1 minus 2e to the 2x times e to the 2x minus 1 all over e to the 2x plus 1 squared. So I have this common factor in the numerator, so I'm going to pull that out, 2e to the 2x, and I'll have e to the 2x plus 1 minus e to the 2x minus 1 over e to the 2x plus 1 squared. So here inside 2e to the 2x, now I'll have e to the 2x plus 1 minus e to the 2x plus 1 and when that simplifies, these guys will reduce, and this whole bracket will just be 2 because of the 1 plus 1. So I'm going to go right to the, I think, probably fully simplified form of the derivative. So I'm going to say that my left side, the derivative, is 4e to the 2x over e to the 2x plus 1 squared. Now, we're going to try to figure out whether that right-hand side is also equal to this same value. So I'm going to make a new slide and we'll go through what 1 minus y squared would look like for that right-hand side. Just as a reminder, we have y equals e to the 2x minus 1 over e to the 2x plus 1. So I don't actually know, I haven't worked this out, I just kind of simplified the derivative as much as I can, and now I'm going to work on the other side, the right-hand side, and say, well, what's 1 minus y squared? So this is going to be 1 minus e to the 2x minus 1. Actually, I'm going to square the top and bottom, kind of like looking ahead. Just like that, squaring each piece. Because I do know that I had a denominator of e to the 2x plus 1 squared. So I think that having like this denominator is probably in my best interest. So that's what I'm going to do. I'm going to common denominator that with the 1 out front. So I'm going to say this is e to the 2x, whoops, plus 1 squared minus e to the 2x minus 1 all squared over e to the 2x plus 1 squared. So now at least I have the denominators equal. If I can make this thing, and this is just kind of my like thought bubble, you don't actually like write this in your proof, but basically I want this top thing to be 4e to the 2x. So I have to figure out whether that's going to be true. And to do that, I'm going to FOIL out these two pieces. So I'm going to square those brackets. So here I've got e to the 4x, because I would add my exponents, plus 2e to the 2x plus 1 minus e to the 4x minus 2e to the 2x plus 1. And that's just multiplying out like e to the 2x plus 1, e to the 2x plus 1, or the minus 1, the same thing. And then just actual FOIL to multiply those out. I didn't show that step. So here I get e to the 2x plus 1 squared. And when I subtract this, I'm running a little bit short on room, but it's going to be okay. I get e to the 4x plus 2e to the 2x plus 1 minus e to the 4x plus 2e to the 2x, that minus a negative, minus 1, over the denominator that I know is what I wanted, which is good news. And then I've got a plus 1 and a minus 1 and a e to the 4x and a minus e to the 4x. I did get a little worried when I had that e to the 4x for a minute there. But here I get 4e to the 2x over e to the 2x plus 1 all squared. So left side equals the right side. So you're doing just a left side, right side proof. Simplify the derivative as much as you can, and then compare it to what you're trying to show that it's equal to. Okay, this one is finding the second derivative. I want to simplify this first. I don't like this cotangent at all. So I'm going to say that that's cos x times cos x over sine x. And then I'm going to write that as cos x. Pick a bracket. It doesn't matter. Not one round bracket and one square bracket. So cos x squared over sine x. So when I do the derivative here, f prime x is the denominator times the derivative of the numerator, which is going to require a chain rule. So this is 2 cos x times the derivative of cos, which is negative sine x, minus the numerator, so cos x squared times the derivative of the denominator, which is cos x, all over the denominator squared. So cleaning this up just a bit. All right, so we're going to have negative 2 cos x sine squared x minus cos cubed x over sine squared x. And common factoring out a negative cos. Here I have 2 sine squared x plus cos squared x over sine squared x. Now you could, I'm running a little bit short on space here, but you could choose, I'm kind of two minds here. Part of me thinks, hey, I could get, like, change that into, maybe say make that like a 1 minus sine squared, and combine it with that. Or I could get the whole numerator in terms of just cos. I think I might go with the 1 minus sine squared. So negative cos x times 2 sine squared x plus 1 minus sine squared x over sine squared x. So negative cos x times sine squared x plus 1 over sine squared x. Now this is definitely one that I would not expect you to be able to factor and simplify because it gets pretty messy. Unless there's something that I'm maybe not seeing, because this definitely there could be a way to simplify this more that I'm not seeing right away, but I wouldn't expect you to be able to simplify this in a specific way on a test. So then if I were to do the second derivative, throwing in another slide here, this would be one where I just said, where I would say just do the first step and don't simplify for the second derivative. So we are going to have quotient rule. So the bottom, sine squared x, times the derivative of the top. And this is going to be a product rule in this derivative. So this will be the first, negative cos x times the derivative of the second, which is 2 sine x cos x, plus the second, sine squared x plus 1 times the derivative of the first. So the derivative of cos is negative sine, but it's already negative, so it's going to be positive sine x. Minus, now we've got the, I'm just going to kind of continue this down on the next line because I'm out of space. So now I'm going to have minus the top, which is negative cos x sine squared x plus 1 times the derivative of the bottom, which is 2 sine x times the derivative of sine, which is cos, all over the denominator, so sine squared x all squared. And again, this is super messy. I would not expect it to be simplified. If you can do the first step, you're good. I may look up in the solutions and see if there's a simplification that I didn't notice, because maybe it would kind of come together in a way that made this more easy to do the derivative of, but I would look at that as a big one that that you wouldn't be expected to simplify. Good question here on the example from the Jamboard. It does not matter if you combine the first two terms. So if you had looked, I said that I was going to look at it as this term as like this one times this one, but it totally doesn't matter. You could absolutely combine like these two. So then you would do the first. So you would do the first terms, so 3x minus 1 to the 1/2 times 2 to the x times the derivative of the second. And then that would be cos 3x cubed times 9x squared, plus, now it would be the second, sine 3x squared cubed times the derivative of the first. Now you would do a product rule again, taking the derivative of those two. So it would be the first, 3x minus 1 to the 1/2. Derivative of the second is 2 to the x ln 2. You're going to get the same things, just in a different order. Plus the second, 2 to the x times the derivative of the first, which is 1/2 times 3x minus 1 to the negative 1/2 times 3. I think that is it. So that is an alternate solution. It looks a little bit different, but it's really the same thing. So I will be available by email if anybody has any problems or concerns, and I will see you guys online at 12 o'clock.